This is the final project presentation for the course CNST 6308, Data Analysis in Construction Management. The title of the project is Using AI Models for Early Procurement of Bulk Materials in FPSO Module Fabrication, by Luzuriaga. Most EPC projects in the onshore oil and gas industry follow a sequence and timing similar to the one shown below, with the overall duration varying depending on the size of the project. In the offshore floater industry, the sequence is pretty much the same, but the timing could be somewhat different due to additional considerations that are not found in the onshore industry. On an FPSO, the hull and marine inputs were an important input to the design of the topsides. Vessel motions introduce stress to the module structures. Those stresses must be considered in the piping stress analysis. Pipe sizing and routing can proceed without much impact since the equipment layout can be fixed early on, and the starting and ending points of the pipe will not change much. While the routing may be tweaked here and there to optimize the layout within the space available, the piping material takeoff will not change very much. The pipe support design, however, can change drastically with a small change in pipe routing. Two pipes may be brought closer together and two smaller supports may be combined into a larger support. Pipe stress analysis may require moving or adding supports, or changing the type of support. Pipe support design is usually finalized after issued for construction. Piping isometrics are complete, usually lagging by a couple weeks. Material should already be on site by the time the pipe support IFC drawings are issued, which means the material takeoff should be provided many months before to allow for the procurement cycle to run its course. But with such drastic changes possible, the 3D model typically uses placeholders for pipe supports and cannot provide an accurate estimate of materials at such an early stage. Delays in material procurement could cause delays in piping installation and module delivery. Therefore, a method is required to estimate pipe support MTO, something that can be done using AI and machine learning. The dataset includes the piping isometric material takeoff and the pipe support material takeoff from past projects. The more information available, the better the models will be able to estimate the required materials. The piping isometric MTO contains a lot of useful information and can easily be grouped by module. Information includes line numbers, total length and size of pipe for each line number, total number of fittings such as elbows, T's, reducers, etc., the pipe material and the service of the lines, such as hydrocarbon, non-hydrocarbon, liquid or gas, etc. If module size was included in the dataset, information about piping density or complexity could be derived, which may improve the model. For our purposes, to keep things simple, the focus is on the length of pipe for each module. The pipe support MTO is available in different formats depending on the source. The fabrication MTO also contained references to the module number and line number similar to the piping isometric MTO. It also has the pipe support tag, type of member for each part of each support as well as the size of that member, and the quantity of material by size and weight. From this data set, it might be possible to correlate the quantity of pipe in a module to the material required for fabricating pipe supports in that module. To do this, we can use regression models to determine the relationship between total pipe and support material for several different modules. Then test whether the resulting estimates are accurate, because the size of the pipe may influence the type of member required for the support. It may be necessary to include information about the size of pipe in the module. For example, 1,000 meters of pipe in a module may result in a different estimate if it contained 800 meters of 2 pipe and 200 meters of 6 pipe versus 200 meters of 2 pipe and 800 meters of 6 pipe. Although, because pipes may be combined to share a support, the pipe size may not need to be a factor. For this study we will look at the weighted average diameter for the module and compare it to modeling with no consideration for size of pipe in the module. For this study, we will focus on 4 common structural members: steel plate, beams, angle bar, and tubular. First we look at the resulting data after being grouped by module from the raw data set. Plotting the total length of pipe in a module against the total weight of a particular structural member for that module gives us the following results. It appears to show that, as the total length of pipe increases for any module, the relative total weight of that structural member increases. As the total length increases, the range of structural weight begins to vary more. You can see this from the shape of the plot, forming a sort of expanding cone from the origin. When plotting the average pipe diameter against the member weight, a much different result is shown. There appears to be no correlation between the average pipe diameter and the total member weight. This may indicate that using the average pipe diameter may introduce greater uncertainty in the results. The results of the regression model using total length of pipe and average diameter as the dependent variables confirm previous expectations. As the predicted values increase, the variance increases. The R-squared values also appear to range from 0.345 to 0.811. This could be due to the lack of data. Although the original data set includes tens of thousands of records, the compiled data set results in less than 100 records for each member type. The results of the regression model using only the total length of pipe as the dependent variable also shows that as the predicted values increase, the variance increases. The R-squared values also vary quite a bit. Additional runs of the 2 models show that the R-squared values can change a lot from run to run. However, the average of 100 runs was calculated and the results are shown here. The average R-squared values for each model are similar, meaning that either model can be used to estimate the material requirement with similar results. In conclusion, data from additional projects can be used to improve the model. Further studies could also be performed that take advantage of the data available, such as type of module, size of module, whether a line is vapor or liquid service. These factors may influence the amount and size of pipe supports in a module. However, with the simple correlation of pipe length to pipe support material quantity, a good enough correlation can be made to procure a certain percentage of the estimate with confidence, meaning that enough material can be made available on site early enough to start pipe support fabrication, while additional top-up orders can be made later to fill in the gap required to complete pipe support fabrication.